Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Introduce my colleague Jim Laris, who is the Director of Research and Strategy within the Extreme Computing Group. For those of you that, many academics here, in fact almost everybody's an academic here. Well, Jim is a former professor from the University of Wisconsin, and before he got lured here many years ago.
Many years ago.
Many years ago. Since he's been here, he's done a number of projects, run the languages and tool groups. He was responsible for probably the first major OS other than Windows out of Microsoft recently, and that's the Singularity project, which has been released to the academic community, I believe. That's right. And now he's been planning our strategy for programming the cloud within the Extreme Computing Group and leading really a research effort. So now you're going to hear about some research stuff.
Right. Thank you, Dennis. Yes, you're going to hear about some research stuff. So it's good you guys heard those two talks beforehand to see where the world is. I'm going to sort of try to anticipate where the world is going, which is what research is supposed to do, and maybe even drive what it looks like when we get there. So I'm starting with the premise that something I'm going to call cloud computing is the next computing platform. You know, cloud computing is this overloaded term. Some people use it to talk about, Amazon, which is a platform. Some use it to talk about Azure, which is, a little more than a platform because there's some software on it. I'm going to use it in a much more general sense. I'm talking about cloud computing as the combination of lots of interconnected devices. Some of them things like, the iPhone, some of them embedded systems, some of them are PCs, plus this vast computing resources that are available to you in the cloud. Some of which can be services like Azure, some of which can be just the existing websites, some of them can be things like Google or Bing or search like that. I'm viewing this whole thing as a computing platform, and I want to talk about sort of how do we get there and how do we make it accessible as a platform for lots of programmers to use, not just sort of elite level programmers like you would see in universities or in Microsoft. The starting point is basically anything can be a client. It's relatively cheap these days to add network connectivity to a device. You can argue about whether we have enough wireless bandwidth, which we don't. But basically, it doesn't cost very much. Think about something like Kindle, this little reader, and it comes with a cellular phone modem built in, just so you can download the books transparently. Okay. So, the starting premise I have is that in the history of computing, there have been a number of these platform changes. And each one of these platform changes has been enabled by sort of new technology, which has driven new software, which has led to radical changes in the way in which we do computing and the players in the computing market. You go back to the mainframes, and really, IBM took advantage of transistors to build the first mainframes around the 360 series, and then the integrated circuits came, and we came with the mini computers, and then VLSI came along, and you were able to put a computer on a chip, and Intel came along, and we had PCs and Microsoft, and then we have cloud computing. So where is that going to take us? Well, I see us as going in this world of a large number of devices. They're not going to look like computers. The PCs are not going away. I don't think any of you could really imagine throwing away all of your computing devices that look like PCs and replacing them with iPhones. You can do a lot of things with iPhones, and you can do a lot of new things with iPhones, but you are not going to sit there and write a paper on one. Apparently in Japan you can write a novel on one, but I don't think most people are going to go that direction. But much more interesting than that is the fact that there are going to be all these specialized devices, and they're going to be part of your network too. And they're really going to depend upon a cloud to connect them together. So, a good example of that, from my mind, is the Kindle. Is that, here's this device that sort of, could be a freestanding device, but it's a lot more valuable because it's connected to the internet. You can go to the website and you can buy a book, and all of a sudden it just appears there. And the web is, or the cloud is what makes it seamless and transparent to the user to use this device. It's a lot more convenient than trying to find the book on the Kindle itself, if any of you have ever tried that. So we're moving in this direction. How are we going to get there, and how are we going to program it? And I'm really focused on the latter question rather than the first question, which is a business question as much as anything. So the group that Dennis and I are part of is the Extreme Computing Group. And what we're interested in is this entire ecosystem, from the hardware that's in the data center through the operating system in the data center, the Azure that you heard about earlier, to the data center software, and I just put a couple examples up there, to the client hardware and the client software. Because this whole thing is the platform. You know, if you think about it, we are going to have to be able to write software that runs in multiple places. So if you're going to write an application, it's not just going to be a data center application in the future if there's going to be specialized hardware around it. And similarly, if you're going to write a client application, what are you going to back it up with? Just public websites? It's not going to have very much functionality that distinguishes it from anybody else's, as we've all seen from the phone app store, where basically any good idea gets cloned and copied in no time at all. So our group, the Extreme Computing Group, is trying to look across this entire stack and basically sort of look for places where there's innovation that can occur, where we can change the hardware and the software at the same time and really develop new solutions there. And I'm not going to be able to talk about all of it today. I'm going to focus on one part of it, which is how do you program this? Or what are the challenges that are involved in writing software for this world? I'm going to sort of quickly march through the challenges, and then I'm going to talk a little bit about the solution that we're building, which is a system called Orleans. So first challenge, and I'd say the distinguishing challenge here, is scale. So think about it. Basically, if you're putting up a cloud service and that's your business, you can go from 0 to 400 million people using your service in the matter of a couple years. And they're all sort of sitting there on your platform, and you're running their software concurrently 7/24 all the time. That's a real challenge. You're basically building the equivalent of, you know, more than the infrastructure of the United States, for more people than are in the United States. And you did this in a couple years, starting from 0. This is a huge challenge because we've made things available. We've provided a seamless network around the globe. And if something takes off, it really takes off. And it has to be continuously available, and you have to figure out how to make money on it. And as our previous speakers pointed out, it's an unreliable platform. So you basically have to assume that things are going to be failing, though you're trying to provide the service. So one idea to see the scale is a little bit about what Dilip talked about. So let me just sort of skip over what he did and just give you an idea. These are the data centers that were current about 2 or 3 years ago. Dilip mentioned that they were the size of a football field. They are. Each one of them has floor space equivalent to about 11.5 football fields. It actually doesn't really matter whether you're talking about U.S. football or the rest of the world. They're roughly the same size. The soccer pitches are actually a little bit bigger, but it doesn't really matter for this point. The Chicago data center Dilip mentioned is 17 times the size of a football field. These are genuinely huge buildings. I mean, if you've ever walked into one of these things, it's walking out of computer science, walking into large-scale industry. I mean, just a different scale of things. And it really indicates the infrastructure and a concrete embodiment of what you have to do to sort of be able to handle the demand that comes around the world. On the other hand, if you look at the programming that you need to do, it's a lot of the same problems that we've been struggling with in computer science for as long as I've been doing it, and even beyond that. You know, concurrency, parallelism, message passing, distribution, high availability, performance, partitioning, defect detection, high-level abstractions. All these things are the same challenges that we've dealt with before. And we don't necessarily have good solutions for them, but we're going to have to go back and revisit them. And a lot of what I'm going to talk about in the next few slides are why these problems are still challenges for us in this space, and why we can't get away from them and can't use the old solutions. So let me start with concurrency. All of you probably have seen this, but the web and the cloud computing is inherently concurrent. Basically, the mode of communication for most of it is messages. Messages arrive asynchronously. You need some sort of internal concurrency to be able to deal with messages, to be able to deal with the fact that messages arrive out of order, that they arrive at unpredictable times. The other thing is that we share resources in the cloud. Basically, one server is processing many, many different users' requests at the same time, and so we have to be able to handle multiple request streams, and so there's concurrency involved in that. This is just a fact of life. You have to write software with this assumption from the beginning. It's not like running desktop software where you can pretty well hide the concurrency. On the other hand, the reason that all this stuff actually works is that, most of this concurrency is essentially independent. It's embarrassingly parallel. We have a lot of it, which is great because we can take advantage of sort of scale out resources, and it doesn't interact very much, so we don't actually have to do a lot of synchronization and sharing. On the other hand, we don't have a great idea of how to deal with concurrent programming. The two ways that people have proposed in the past are basically threads or events. So do you handle a request by giving it a thread and allowing it to block when it's waiting for something to occur? Or do you write event handlers that get fired when a message arrives and the next step of the processing goes? They're both perfectly reasonable ways of handling concurrency. They've been used in different systems to different degrees, and sometimes they're even intermixed together. They have their advantages and their disadvantages, but neither one has ever been able to win the war over the other one. And so what we have is we have this fracture where some people belong to this camp, some people belong to this camp, some languages come here, some languages come there. And it makes it very, very hard for us to teach people how to program this kind of concurrency because there's not a single model we can start with. And it makes it very hard in some cases to share code because it's very difficult to translate between one model and the other. There's also been a lot of interest in higher level models, state machines which abstract away from the details or actors. There's very little consensus about these models and whether they're actually a good idea or not. I would argue that this is one of the sort of real key areas for us to focus in on because the lack of consensus in this area makes research difficult because part of the world is going in that direction, part of the world is going in this direction, and we've been going in those two directions for 30 years without kind of any resolution. It makes it hard to do development when some of the people want to go this way and some want to go that way. Reuse is obviously difficult as well. You know, do I think that there's an answer to this? I'm not sure. I think I used to believe in one side or the other, and I can tell you in my career I've chosen both sides and changed my mind. But these days I'm actually much more interested in the higher level models, and the reason for that is that I look out and see the vast world of programmers, many of whom have no experience in concurrency because they grew up on simpler environments, and I say, how do we move them into this world where concurrency is inherent? And I think the answer is higher level models, and I'll talk about ours a little later. There's also parallelism in this world. Basically, as Dilip indicated, all the machines that we use are parallel machines. This is the way the world's going because we've run out of the ability to increase the clock speed, so things are just becoming more parallel. And I think in the future they're also going to become more heterogeneous because if you really want to use power efficiently, you design functional units that do one task and do it very well. And in the data center, there's a lot of room for this kind of optimization. If we're really concerned about efficiency and cost and power, we can do specialization on the computer, which means that the data center is not going to be a collection of uniform machines that are identical to each other. Parallel programming, I don't need to sort of bring this up in this audience. It's a long-standing challenge for the community. We've been at it for a long time without really sort of coming to any kind of consensus or resolution on it. My proposal in the data center is basically to get rid of one form of parallelism, which is the shared memory parallelism, and basically just say, we have to do message passing between machines, so let's do message passing on a machine as well. Let's just basically simplify our life, get rid of one way of programming parallel machines, and concentrate on the one that we actually have to have. And I'll explain how this actually works in the model that I have a little bit later. Message passing, little to say there except that there has been too little language support for message passing in the past. Message passing is typically a library you load into a language that has sort of bindings, and it doesn't actually work all that well because it's asynchronous in a synchronous language, and that's a difficult thing to do. I think that there are languages where it has been integrated which actually show the way. Erlang, for instance, integrates messages with the pattern matching in the language in a way that's very nice and it makes it very easy to write the message handling code by just pattern matching on the contents of the message. In the Singularity language, Sing#, we actually looked at putting contracts on the messages so you could write the protocol and we could statically analyze your code to make sure you handled all the cases that would arise in the protocol. And that found a lot of errors in our code as well. There are lots of things that could be done. I think this is a great area for us to focus in on as a community. Let me skip this to save some time. Next real challenging area in building this kind of software is distributed systems. Everybody knows we're building distributed systems. It's been a great research area for the community. They've come up with some very, very powerful techniques of for replication, consistency, and quorum consensus. They're also not easy techniques to sort of give to developers who aren't versed in the art. So how do we hide the complexity of these techniques but make them into routine programming tools? It's a real challenge because, for instance, just take something as simple as replication. As soon as you replicate your data, and that's what you do to avoid failure or to get better bandwidth out of a particular part of your system, once you replicate it, as long as it's changing, you have this problem of consistency. We're all used to a world in which you write something and you read it and you get back the value. But suppose you wrote something and then read it and you didn't get back the value. Could you live with that? Are there parts of your application that you could live with it? Are there other parts where you absolutely can't live with that? Most people don't think about things that way yet. You're going to have to in a distributed world. And another issue, obviously, availability. If you're building a service that is used by a large number of people, you need to make it available all the time, in spite of the fact that it's running on a failable platform, in spite of the fact that the networks that connect it to users are failing as well. It's a real challenge because it requires engineering to actually do this, and it requires a lot of operator discipline. That's why a lot of people, I think, are going to end up depending upon services like Azure, because a lot of the discipline of actually keeping the system running can be outsourced to an organization like Microsoft or Amazon or somebody that actually specializes in it, and that's difficult to do. On the other hand, you actually have to build the underlying software to tolerate failure, and that's something we don't really know how to do all that well. If you look at failure handling in programming languages, it's a real source of errors. Previous to this, I was looking at software defects for a long time at Microsoft. And we found a lot of errors in the error handling code. And it's just natural. It's the code that gets written last. It's the code that doesn't get tested very thoroughly. It's the code that's very difficult to write because the state of the world is very confused when it's actually running. But if you're actually going to handle errors and continue operating, that's the code that has to work. How do we incentivize people? How do we give them abstractions that allow them to write reliable systems in spite of the fact that pieces of the system are failing? How do we handle errors in a way that's easy to understand and makes it possible to do it in a successful way? These are programming questions. Performance, all of you sort of probably believe performance is less of an issue. It turns out that when you move into this space, performance becomes a different issue. It's no longer so much the performance of one core on a machine that matters to you, or the low-level performance of the central part of your algorithm. Things that you've never thought about before, like the performance of the TCP/IP stack, start mattering a lot to you. The fact that there are packets colliding and that they're colliding at the machine that's receiving them, or they're colliding on a single Ethernet segment, start to dominate the performance of your system. So, how do we make this either transparent to people so that it doesn't occur, or how do we make it so that you can actually understand what's going on in the many levels of abstraction below your software that are on the system? Because one of the things that we're doing is making the software stack under you a lot more complicated. It's not only the operating system and the network stack on the machines that are running there, but it's also the entire operating system and network stack running on all the switches in the data center as well. And those are written by somebody else and have very complicated behaviors as well. So how do we teach people to do this? How do we also teach people to architect software that's going to scale? So you're fortunate enough to start up a new service and it becomes wildly popular and you go from 0 to 400 million customers. How do you write a system that you don't have to throw away and rewrite continuously to keep up with the growth. That's a challenge. This is scale out is an easy thing to say. It's a difficult thing to achieve. I talked about the rich clients. How do we partition the application between the client and the server? How do we partition the application so that you can have clients of widely different power or compute ability or memory and still use the same code across different clients and on the server side, so that you don't have to rewrite your code for every new client that comes along? Right now, there are two fundamentally different applications, and they're basically just connected by a sort of high-level protocol across the wire, an HTTP protocol typically. Is there a better way of doing it so you don't actually have to write these as separate applications and deal with the divide between them? Errors, yeah, there are going to be lots of errors in the system. There are going to be a lot more complicated errors because they're going to occur not only on the machine you're running on, but on lots of other machines, many of which you may not even know about in the data center. How do you reflect these errors back into the programming model in a way in which developers can actually understand them? So high-level abstractions. I think this is another sort of key challenge for the programming community. All of you are probably familiar with MapReduce, which has turned out to be a sort of wonderful abstraction for talking about a particular type of computation, typically a large-scale data processing problem. It works very well for that. But there are a lot of other things that go on in cloud computing, in particular in the interactive applications that don't fit into the MapReduce paradigm. But is there a similar high-level paradigm that we could use to describe this type of interactive computation, where people could write small parts of it and the runtime system could handle large portions of it and relieve the developers of the complexity? I think that's a central challenge in making cloud computing successful. Okay, so I'm a programming languages guy, so the answer to all these things is clearly it's a programming problem. My advisor had this slogan. He basically said, when you're got a hammer, everything looks like a nail. So I started with programming languages, and so everything looks like a programming language problem to me. The system that we're building right now is called Orleans. Basically, it's a framework that's built on top of .NET, and its goal is to provide a simple, widely accessible programming model. And widely accessible means accessible to the vast majority of software developers. We're not aiming at sort of people who work for Facebook or Twitter or Microsoft. We're aiming at sort of the large number of people who want to build scalable web services. We're trying to encourage the use of a software architecture that's scalable and resilient. In many ways, what we're trying to do is raise the level of abstraction. So those of you who are familiar with Windows know that there's the CLR, the whole .NET platform that sits on top of Windows. It gives you a higher level programming model, a much more safe programming model, safe programming languages, garbage collection, vast libraries of functionality that make it a lot more efficient to write code. So what we're trying to do is we're trying to provide the CLR or the .NET platform for cloud computing. We're sitting on top of Azure instead of Windows because Azure is the operating system for the data center, and we're trying to give you the higher level programming model. The model we started with is a fairly simple model called actors. Many of you have heard it. It's been around for a long time. We call the actors grains, which are units of computation. They basically encapsulate some data, and they have a computation in it. We can move the grains around both within and between data centers. They were designed to be easily migrated right from the beginning. All the issues about replication and consistency and persistence of grains are handled by the runtime system rather than the user. These are sort of orthogonal concerns, building blocks that you use to build these systems, not things that you should have to implement in your code. Another thing about the grains is that they have a very simple concurrency model. Each one of the grains is single-threaded. It gets a top-level request. It processes it to completion. When it's sent the response back, it gets the next request. We don't try to have concurrency within the grains. So we don't have to worry about locking of the data structures within the grains. if you want concurrency, basically, for your system, if you want to get throughput in the system, you replicate the grains. We have different activations of the grain. And each of them is processing a separate request, and so we get concurrency that way. But they're isolated from each other, so in many ways they're like transactions in the sense that you don't really care what else is running at the same time in terms of these grains. Obviously, there's an issue if you have multiple activations of the grains that are changing the shared state. We have to worry about making that shared state consistent between the activations, and we do. We have a simple transaction-like model that allows us to ensure that the state remains consistent, even though it's being modified by multiple grains at one time. We're developing one programming model for both the client and the server side of things. And so the idea is that you write your code using grains, regardless of whether the grains are going to run on the server or the client. And in fact, we are experimenting with dynamic binding so that the assignment of a grain to the client or the server side can be done at runtime, or we can actually, hopefully someday, migrate them between the client and the data center, or the data center and the client. So here's a picture. Basically, you can imagine, your data center is there running on Azure. There's the Orleans runtime, and the blue things in there are grains, and within each of the grains there are activations, which are the black instances of the grain. They communicate using messages, and on the clients over there, there's similar Orleans runtime, probably a little lighter weight than what we would have on the server. And it also has the same programming model, and the communication occurs between them. And then on top of that is the application code, or basically the application code is built using these grains. And so this is a fairly simple model. Hopefully, we can provide a lot of functionality in the libraries that go along with Orleans as well, so that you don't have to write nearly as much code. And we've been experimenting with building some fairly large functionality libraries, for instance, for handling very large distributed graphs, which seem to come up very frequently, for instance, in social networking, to represent the connections between the users. The architecture of the Orleans runtime system is basically to take a lot of functionality that we see people implementing again and again across all of the different cloud computing applications and bring it into the runtime. So things like geodistribution, where you basically want to run your computation on different data centers so that you're tolerant to the failure of the data center, or you're located closer to the user so you reduce the latency of communication to the user. Performance monitoring, basically. How do you know what your system's doing? Well, the only way you're going to know what's actually going on is to continually monitor the performance. That's a very challenging task for a distributed system because there are a lot of separate pieces running, and the volume of data you collect is huge. Correctness monitoring, same thing, basically. There's something which is called a gray failure, which is an interesting concept, which basically, for one of these systems, means that part of your system has failed. You're not aware that it's failed, but it's affecting the behavior or the performance of your system, and you have no idea how to fix it. And this apparently occurs fairly frequently in this world, is that literally failures occur and nobody notices them. At least nobody who's running the system notices them. I think the consumers of the system typically see the side effects of them. Data replication and consistency, I already sort of mentioned the sort of key and central importance of this in building reliable systems and building high-performance systems. If we couldn't replicate computation and we couldn't replicate data, we couldn't build this kind of system. But once you've replicated, you have to worry about consistency. And we would like to sort of raise that out of the level of the code that a developer has to write and make that something the system provides as a service. Adaptive control. Can we actually build control systems that can watch the behavior of your system and adapt to it? Can we grab more machines from Azure as the load goes up? Can we release them back to Azure as the load goes down? Can we handle failure by invoking recovery routines? That's adaptive control. Debugging, a huge problem. And then a lot more prosaic issues, things like deployment. How do you deploy? What is an application? How do you deploy it across a large number of machines in a data center? What happens when a new user comes on board? How do you configure a system? How do you change the configuration? How do you do maintenance on a system? Have you ever thought about how do you upgrade a service that's running 7/24 on a data center? Do you do it one machine at a time? Do you do it in one big chunk? Do you what happens if you get halfway through and you realize there's a bug in the upgrade? Can you roll it back? These are very, very challenging engineering problems, and the type of thing that really needs to be solved well and solved once so that people can build on top of it instead of pushing the responsibility to every developer. So another view of it is, let me just sort of skip that. So I think this one is actually probably a better picture of what we're trying to provide. So the idea with these grains, which are the ovals here, are that we're going to provide a number of different services to them. Things like replication, so you can have multiple instances of grain, migration, persistence, we'll be able to store them in stable storage, and then also mobility. We'll be able to move the grains to either do load balancing within the data center or move them onto the client device or off the client device for various reasons. You can imagine starting a computation on your cell phone, and then the data is not local. It would be more efficient to move it to where the data is. Jim Gray's paradigm, move the computation, not the data. Or you realize there's not enough battery power on your cell phone to complete the computation. You move it into the data center to finish it and then bring back the results. Lots of different scenarios are enabled by mobility. Big deal in this is really separation of concerns. Can we separate the abstractions, the ideas that you need to build this type of application, from the code that the user writes? If we can, then there's a hope that we can actually bring in a large number of programmers, teach them about these abstractions when they're ready to be used without having to feed them through a distributed system course, and teach them how to write all of these abstractions as part of their code themselves. Another big issue we've been struggling with is how do you compose grains? So, I build a service that's based on grains, you build a service that's based on grains. How do we put them together in a way in which preserves the desirable properties of both of them? Do we just wire them together by exchanging messages? Is that done externally with some sort of manifest, or is it done by just like TCP/IP, where you connect to a particular port on a service? The life cycle, for anybody who's actually gone and built a service and actually run it, this is the biggest challenge. It's easy enough to do the code development, but to keep the service up and running and maintain it is a huge engineering challenge and a continuous engineering challenge, and something that really needs to be shifted onto the platform rather than the individual applications. Another interesting area, which I think is an open area, is cloud tools. So the tools we have for debugging and finding errors in systems do not scale to anything near what we have. How do you debug 10,000 machines in a data center that are running, say, 1 million separate tasks, all of which are independent, only some small fraction of which are failing at any one time? How do you even identify where the failures occur? How do you identify performance bottlenecks in a system of this size? How do you find them? How do you monitor them so that you can see hardware failure or attacks on your system? There are very, very few tools that are addressing scale at this issue. And by tools, I mean either things that come out of the research community or things that are sitting in commercial operating systems like what Microsoft or our competitors has. They just don't exist yet. Let me skip a few of these. So, in conclusion, basically, I'm taking the term cloud computing and tried to raise it to a higher level than what most people use it at. Most people think of it as a fairly prosaic thing. The platform as a service that Amazon provides, or the services that Microsoft provides. Basically, the sort of low-level infrastructure that allows you to get started. I actually see cloud computing as a much more interesting thing, this combination of vast computing and data resources that are available across the networks, and a profusion of very interesting clients that are coming up that are connected together. This is a platform. This is a new platform. This is one that opens up lots of great challenges. There are a lot of things we can do with the this platform, one of my fondest hopes is that we can actually correct some of the mistakes we made the last time around when we built all the software that we use day to day, whether it's on PCs or Macs or everything else. There are a lot of bad choices we made back in an era of much more limited resources that were impossible to fix. My hope is that this time around we can actually sort of learn from our mistakes and build a platform that's much easier for people to use, much more resilient and tolerant of people's mistakes and failings, and make it so that computing is much more natural for the rest of the world that doesn't have a computer science degree. I see this as a great area. It's a huge challenge for the programming languages, the compilers, the distributed systems, the operating systems, you name it, computer architecture. The entire computer science research community really should be getting around this and seeing this as a source of new problems, new challenges, new things that you can actually address using a lot of the same techniques that you've seen before, but a lot of new contexts and a lot of different issues of scale and reliability and continuous operation. So I think I have a few minutes left for questions.
Yeah, the cloud computers you're talking about are about 1/30 the size of, say, Blue Waters. Are there lessons we can learn from HPC that would apply to clouds?
That's a very good question. I don't know enough about the sort of detailed lessons of what the HPC community learned from running on that scale of system to exactly draw analogs. I would assume that some of the challenges they faced are the same challenges. I know some of the solutions they did, like checkpointing, don't really have an obvious analog in this world. On the other hand, I think in many ways the challenges are different in this space. They're easier because you have a huge amount of embarrassing parallelism, but it's essentially independent parallelism. While on a machine like Blue Waters, most of the processors are dedicated to running one particular computation that's very much tightly connected. And I think one of the advantages we have is that you can fail on one little computation and continue running the rest of the system and still get useful results out of it. So I think it's an interesting direction to look at, and there's probably a lot of engineering that was done on the actual hardware that would be relevant to pull into the data center space as well.
Yeah, I think there's a lot of interesting issues because trying to keep 300,000 machines running is next to impossible. So they will be running with a large number of machines that have failed and have problems. So there's a lot of commonality between...
In the data center space, that's just taken as an assumption and a given, as you heard from the earlier talks, is that you just start from the assumption that some part of what you're going to want to do is either not available or fails while you're actually trying to use it. And you also try to work forward from there.
Yeah, the flip side, it's almost impossible to back up 300,000 machines.
Yes.
Thank you for the great talk about the challenges within the cloud computing. In fact, you have laid out a very good list of all the challenges that we have from distributed computing and high-performance computing. And maybe some of them could be addressed within the cloud platform. I have a question regarding how do you, as a platform designer, developer, provider point of view, how do you define the responsibility of the users, the programmer, and the platform providers? Who's going to take care of which part? The reason I'm trying to ask is, for example, if I'm a user and cloud is supposed to be pay as you go, and I have a, let's say, scientific problem I want to put on the cloud, but I don't know how much computing capability I need. I don't want to explode my wallet.
Yeah. Yeah, those issues of, around the business model, the pricing model, and so forth are, I think in flux right now. I mean, we've started with fairly simple models, basically a certain number of cents per CPU hour, and we basically put all of the burden onto the user to figure out how much they're going to need and probably given some tools to limit it. But in the future, I think that we're going to move to much more sophisticated pricing models, because that model doesn't give us as the cloud provider any indication of how important your computation is to you and how much you're really willing to pay to get enough resources to finish it, which means that we can't really use our data center as efficiently as we want to. You know, we would like to know which jobs are really important that we actually have to dedicate resources, and which ones we could do best effort, and which ones we should just run in the background as just sort of noise computations to soak up cycles. And so I think that the world is going to move in the direction of much more interesting contracts between the various levels, where you know, some of the contracts are going to be monetary. Some of them are going to be things like service level agreements, where we specify a desired level of performance as well.
I think we just have time for one more.
So, Jim, you have a very exciting vision of what cloud computing of the future can be. I'm reminded of what's happened with the global telephone network and the internet. And there's a notion of universal bearer service that has allowed these things to both grow and expand. And there's also the importance of agreed upon protocols. The International Telecommunications Union publishes protocols that every telephone company in the world has to conform to. The IETF has its sets of protocols. Can you see a parallel for having uniform protocols so that people can interoperate with their services in this kind of view of the cloud?
Yeah, I think actually now there are some de facto styles of protocols. I wouldn't call them protocols because I don't think they're formally specified. So things like the SOAP protocols, which allowed you to do remote procedure call between different systems, and then things like the REST interfaces that people build, which allow you to at least talk at a certain level to a system, regardless of what hardware or software platform it's running on. You know, the higher level protocols, which actually start involving the semantics of the application, are obviously a lot more challenging, but essential to building interoperability. You know, I hope that we get enough experience that we can actually start talking about that and start, you know, assembling higher level building blocks to build our software. You know, if you can basically sort of take a large unit of functionality, like, you know, here is a billing service, so that, you know, in building my application, I don't have to worry about billing, just like I don't have to worry about authentication if I run using Microsoft's Passport. You know, those are the components that actually could allow people to build new ideas very much more efficiently than they can now. Because building something like a billing service is a huge amount of work. And it's the kind of thing that people do over and over again. And, you know, that's the level of interface that I think we should be working towards in the future.
All right, I want to thank Jim once more. Thank you very much. Now, our next speaker is Jimlin. He's an associate professor from the iSchool at the University of Maryland. He's done a lot of great work with on the application side and looking at MapReduce computations. Now, he is up against Avatar at 4 o'clock. And so we want to, I'm not going to say any more, let him get started.
Yeah,
so
you took away my opening line, so I'm the one that's standing between you guys and Avatar, so I don't think this is going to be quite as interesting, so I'll try to keep on time. The second thing I realized is that the order of the talks was actually should have actually been flipped around. I should have come up here and told you what we're doing now, and then Jim can offer his vision of the future. We have to, I didn't realize. Yeah, I can start from here also, okay. Okay, so I renamed the title of my talk slightly, Embracing the Data Deluge, Data-Intensive Computing for the Masses. Okay, so a little bit of background. I come from a text processing background. I work on natural language processing, information retrieval. So I'm going to be approaching cloud computing more from the applications end. So the starting point of the talk is quite uncontroversial statement at this point, is we live in a world of large data, and to stay relevant, we got to embrace it. So in my own area of text processing, over the last couple of decades, we've seen the emergence and dominance of empirical data-driven techniques. And so if we don't keep up with the tide, we get reviews back on our papers that say, oh, this is an uninteresting result on a toy conclusion, uninteresting result on a toy data set, reject, or the other alternatives, we spent way too long waiting for our experiments to complete. So neither are good alternatives. In the area of the natural sciences, we've talked about quite a bit at this faculty summit, the emergence of the fourth paradigm, data-intensive e-science, and I'm happy. That makes me happy because there are difficult computer science problems there, and that's job security, right? So what I'll be doing in my talk is presenting 2 case studies of how do we practically scale up to large data sets. I'm going to present a case study from my own area of expertise in natural language processing and statistical machine translation, and I'm going to talk a little bit about some work I've been doing with colleagues in bioinformatics about DNA sequence alignment. Okay, so let's start with a basic question. How much data is it really out there? And so this is a slide I actually have to update quite frequently. I just updated a few months ago. Facebook came out with this statistic that they're storing 36 petabytes of user data, probably most of it not useful. And it's growing about 80 to 90 terabytes a day. CERN's LHC, the Large Hadron Collider, last time they turned it on, they had what my physicist colleagues called a high energy event, which is a euphemism for an explosion. I've heard that's been fixed now, so any day now, the spigot will be turning on and we'll be getting 15 petabytes a year. The astronomy community with the LSST, which is going to come online in 2015, isn't very far behind. They're estimating 6 to 10 petabytes a year. And so whenever I talk this slide, I have to bring up a picture of this guy. Anybody recognize who this is? This is Billy G, right? So it wasn't that long ago when he said, 640K ought to be enough for everybody. And I can imagine somebody standing in the same place maybe a decade or two from now saying, wow, back then, 2 terabytes, 2 petabytes, that's it? Okay. All right, so what do we do with all that data? So for those of you in the audience that are Perl hackers, this is basically what we do. When in doubt, instead of trying to be smart, we simply throw more data at it. Okay, so I'll give you a couple results that are sort of that sort of highlight what I'm talking about. So this was a work actually done at Microsoft Research about 10 years ago. This is a very simple supervised machine learning task. On the x-axis here, we have the amount of training data. This was, I believe, grammar correction, but the task really is not relevant. On the y-axis, we have simple accuracy, and we're plotting the performance of different machine learning algorithms. So the important thing to take away is that, well, it really doesn't matter what algorithm you're working, as long as you give it more data. One, the performance uniformly increases, and second, the performance basically converges. And so the controversial statement at that time was that, well, we should just all quit our jobs and go out and gather more data. Right. So fast forward more recently, there's the similar results published by Google in 2007 with large-scale language models for machine translation. They basically have the same experimental setup. They have language models trained on increasing order magnitude of data, and they have some figure of merit, in this case measuring machine translation accuracy. Holding everything else constant, the more data you throw at it, performance increases. And so there's this joke I like to say in the text processing community, there's basically only one graph. It looks like this. So we draw the graph first, and we just fill in the scales later, right? Yes, you can sort of squint and say, yeah, the slope is decreasing a little bit, but it still has remained true as far as we observe. The more data you throw at it, the better your algorithms get. Right. So the focus of what I've been really thinking about the last few years is, well, how do we get here if we're not Google, right? And so cloud computing is, of course, the answer. And so what is the path to data nirvana? And I think this is sort of my take on it. So with the advent of cheap commodity clusters and utility computing, the previous talks you've heard about in this session, combined with simple and distributed programming models, you get data-intensive computing for the masses. Okay, now you might be a little bit skeptical at this point. I mean, haven't you heard this story before? This is simply the parallel processing, parallelism is a way of the future story that's been told for the last couple decades, right? So why is this different? Well, so let me try to explain why. So parallel computing is hard, and that's the only way we can scale up to large data sets, right? These are just some of the things that we teach our students. Fundamental issues, architectural issues, different programming models, common problems, different programming constructs, etc. But when the rubber meets the road, the reality is that the programmer shoulders all the burden of managing concurrency in traditional programming paradigms. And I'm not happy with that. I don't like that from an applications point of view, because I want my students to be developing machine learning algorithms, not debugging race conditions, right? So this is, and so if they're not careful, they get into jams like this that then I have to come and fix or help them fix, right? So what's the problem? Where do I place the blame? I sort of say this tongue in cheek, but this is where I put the blame in. Right, so this is a standard von Neumann architecture. And the problem is this is what's been guiding us over the last half a century. And as we move into data centers, as we move into the multi-core world, well, what have we done? Well, we've simply taken this and cloned it n times in an entire data center. And so we're still managing all the details at the level we shouldn't be at. And so this is the wrong approach. And this isn't actually a new message, right? This is the same that you've heard reinforced several times throughout the day. We should be thinking about abstractions at the level in an entire data centers, right? So Luis Barroso was a person who said it. The data center is the computer, and we should be thinking of it as such, right? Okay, so this is where MapReduce comes in. So I realized over the course of the last couple of days that not all the invitees to the summit are from are computer scientists. So for the benefit of those that are non-computer scientists, let me just spend a couple of slides talking about MapReduce and what I think is important about it. Okay, so MapReduce in a couple words is functional programming meets distributed processing. It's sort of a generic recipe of that has two steps. So there's one parallelism step in which there's a per record operations you do in parallel, and then there's a reduce step where you aggregate some intermediate results to generate final output. So in a MapReduce programming style, the programmer specifies two functions, a map and a reduce. They operate on key-value pairs. So a map takes an input key-value pair and generates any arbitrary number of intermediate key-value pairs. The reduce, on the other hand, you can imagine as a big group-by operation. All the key-value pairs with the same key get grouped together, and then a reduce computation happens. And the nice thing about it is that basically, from a developer point of view, you specify the map and the reduce, and that's it. Well, not quite accurate. There's some other things you have to specify, but that's about it. And the execution framework handles everything else. Right? It handles scheduling, it handles data management, the transport, it handles synchronization, it handles faults and errors, and all those complex things that I put on a few slides back. Right, so here's a picture of how MapReduce works in animation. So you have input key-value pairs. You run them through a mapper. You get some intermediate key-value pairs. There's this big sort and shuffle dance in which all the values are aggregated by key, and the reduce computation happens to get you some final output. Okay, now, why is this good from my point of view? Well, it's good from my point of view because from the developer perspective, the data center becomes a black box. Literally, all I have to give my students is the access to where the master submit node is, and that's all it is. Right? They write their programs, they submit their jobs on the cluster, and things magically happen. It's a black box to them. Never mind that behind the scenes, the framework, the execution framework, is managing a whole bunch of complex operations, scheduling the individual workers, moving the data around, and all those issues I talked about before. And this makes me very happy because, well, I said earlier, I want my students developing new machine learning algorithms, not debugging race conditions. Check. Right. Okay. So a little bit more about MapReduce. So Google has a proprietary implementation in C++, plus bindings in Java and Python and a couple others. Hadoop, which is this guy, this yellow elephant, is an open source implementation in Java of the programming model. Development was led by Yahoo and is actually used in production by Yahoo. It's now an Apache project, and what excites me is there's a rapidly growing software ecosystem around it. And beyond Google's implementation and the open source Hadoop implementations, there are lots of custom research implementations. So there's MapReduce for GPUs, there's MapReduce for cell processors, and any type of, even for FPGAs, so any type of hardware you can think of. Okay, so let me talk a little bit about my first case study in statistical machine translation. Okay, so let me give you a run through of how modern statistical machine translation works. So it's all data driven, and it's dependent on two types of corpora. So you want to get your hands on a lot of what we call parallel sentences, which are translations of sentence in one language to another. Where do you get them? You get them from places like the United Nations, in which documents are disseminated in multiple languages. You get them in, for example, the Canadian Parliament, where everything is in English and French. So that's one source of data. And the other source of data is target language text. For most of these applications, they're translating into English, and so the target language text is just, you can just crawl the web, basically. Okay, so you take the parallel sentence, you run them through an alignment process using an expectation maximization algorithm. And what that basically does is fill in correspondences to the best of its knowledge between words in foreign language and words in the language you're trying to translate into, which is English in most cases. And from that, you extract these phrases. The phrases having absolutely no linguistic meaning, the phrases just indicating consecutive sequence of tokens. So you learn these patterns that this consecutive sequence of tokens in this language tends to map it in that language from the word alignment process. That goes into what's called the translation model. On the other hand, you take the target language text and build a language model from it. So you probably assign a probability distribution over text in your language. Okay, and that goes all into the decoder, and from there you basically have your machine translation system. In comes a foreign, unseen input sentence, and out comes the translation. Okay, so how does this work? Well, translation, you can think of it sort of as a tiling problem, right? So you start off with your foreign language sentence. You go up in your phrase table, that's up in the right-hand corner there, and you sort of look at all the possible translations that the phrase can match. And what you're trying to do is you're trying to find you're treating it as a tiling problem. You're trying to find a covering of the foreign language sentence that maximizes the probability of being a good sentence in the target language as determined by the target language model. Right, so in this case, it might be something like a path through this, and you accomplish this through something like beam search, for example, and this would be a good translation. Okay, so you throw data at the problem. What are the effects? So here on this graph here, I have a corpus size. This is training data size in terms of number of parallel sentences. And on the y-axis here, you have just a figure of merit of how good the translation is. So you see in the squares on the left here, you have the amount of time it takes to train up the model. So in the solid squares, you see, of course, as the amount of data increases, the training time goes up. And of course, as you give it more data, the translation quality improves also, holding everything else constant. And so this is a great time to bring this quote, a quite famous quote from a colleague in the field, Fred Jelinek. He says, famously said, every time I fire a linguist, the performance of our system goes up, in the sense that this requires absolutely no knowledge about language. All right, so what we've done, what the students have been working with have done, is build MapReduce implementations of these two components. So let me give you some evaluation figures to give you a sense of what's going on. So we focus in particular on the word alignment problem. And so there is an existing open source toolkit that you can go out and download right now. It's called Giza. And here is its performance profile. So here on the x-axis we have size of the collection. On y-axis we have training time. This is an iterative algorithm, so typically you run maybe half a dozen iterations. So the training time on a single core commodity server is on the order of an entire day. So we built a MapReduce implementation of it and got essentially a performance profile of something that looks like this on a 38 processor, 38 core cluster. So iteration goes from about 3 hours to about 3 minutes. Now, of course, this is not fair, right? Because you're comparing a single core against a 38-core processor. And so what I've shown in this graph is taken simply the top line and divided by 38 to demonstrate what the ideal scaling characteristics would be. So the thing that you notice is, well, with a MapReduce implementation, we're not that far off from ideal parallelization. The difference between 3 minutes and maybe 2 minutes, 2 minutes and change. And you really only care about large data because that's the condition we want. We want to throw all the data we have at it. Right, so what's the point? Well, the point is that this mythical optimally parallelized version doesn't exist. Right? Whereas on the other hand, I think the argument we make is that MapReduce occupies a sweet spot in the design space for a large class of problems. Has this 3 nice properties. It's fast in terms of running time and its scaling characteristics, pretty close to optimal. It's easy in terms of programming effort. This whole re-implementation was done on the order of months. And it's cheap in terms of hardware cost and being able to utilize commodity clusters. And so this is work we published a couple of years ago, so this is pretty old news by now. Okay, the second case study I want to talk about is a more recent work by Michael Schatz, who just defended a dissertation on this a few months ago and just graduated, about DNA sequence alignment. Okay, so to explain the problem, let me start with an analogy. Okay, so that's, say, Dickens, in writing A Tale of Two Cities, wrote it in a very weird way. He wrote it on a long spool. It's a long single spool, very, very long. So it was the best of times, the worst of times. You of course realize that this analogy is somewhat tongue-in-cheek because it breaks down very quickly. Right? So that's also assumed that Dickens happens to have backups on 4 more copies. And so you have all these spools. And as he's going to the publisher to get these spools printed, he trips and, oops, he accidentally shreds the manuscript. Okay, now he's got a problem, right? So the problem is, can he reconstruct the text? Right, so you have these little tiny fragments, and copies from each fragments from each of the copies are mixed together. Some fragments are identical, like these. So can he put the manuscript back together? Well, you can think of maybe something like a greedy approach to putting the manuscript back together. You start with all the little splices, and you say, okay, let's line them up. Let's take one of them. And you know that the writing has to be from contiguous spans. You say, okay, that's fine one that sort of overlaps with it, and then with another one that overlaps with that, and then another one that overlaps with that, and so on and so forth. Of course, then you run into this problem of, well, what if you get to this? Right, so in Dickens, the text goes, it was the best of times, it was the worst of times, it was the age of wisdom, it was the age of foolishness. So you have this repeats. And so right here you have a point of branching where it's unambiguous what the next part should be. So the repeated sequence makes the correct reconstruction ambiguous. So the approach that bioinformatics people have developed is to treat this problem and view it as modeling sequence construction as a graph problem. Okay, so let me explain how that works. So what you're going to do is this is called the brain graph construction approach. What you're going to do is you're going to take every original fragment and you're going to create 2 vertices and an edge out of it based on the overlap. Okay, and so what you do here is you're creating local graph structure, and implicitly you're revealing the global graph structure. And I can show that very clearly in this animation here. Right, so once you do that to all the segments, you get something that looks like this. Right, so then you can clearly see that an Eulerian tour of the graph reconstructs the original text. However, you still have the problem that there may be multiple tours, and so that's the issue there. And so having a unique Eulerian tour, what you want to do is simplify the graph as much as possible. Okay, so I've basically given you an overview of modern DNA sequence alignment. All you have to do now is take text construction and turn it over into DNA sequences. Okay, so this is a real problem. This is what happens. So you start with a subject genome of somebody that you want to sequence. This maybe from a blood sample, from a cheek swab, something along those lines. Run it through sequencers. Here are some examples of what sequencers look like. And you get a whole bunch of these snippets, right? In A, T, and C, and G, the amino acids that make up DNA, right? So the joke I like to make is, well, that's kind of like text processing too, right? They just have a smaller alphabet. Okay, so what you get out of it is a unique human genome is about 3 giga base pairs, and out of these sequencers, you get about a few billion short reads because there are overlaps and there's duplication, and so all in all, it's about 100 gigabytes of compressed data. Okay, so what's the present solution of stitching all of these back together per the previous slide I talked about? Well, the present solution involved large shared memory machines or clusters with high-speed interconnects, InfiniBand, et cetera. Right? So there are papers talking about bringing clusters with a few terabytes of RAM or half a terabyte of RAM to bear on the problem. And Mike's dissertation focused on this alternative. Can we get by with MapReduce on cheap commodity clusters? And the answer is yes. So I'll show you a small part of it. Okay, so as it turns out, the most important problem from a computer science point of view is this graph compression problem. You want to take this really large graph that has a lot of small individual sequences and compress it down to something that looks like this. As it turns out, without knowledge from biology and the biologists getting involved, this is pretty much the best that you can do because in a human genome, there are lots of repeated regions. So for example, you can go into this loop and go around hundreds of times sometime. So you need to get the biologists involved. So the challenge is working in a MapReduce framework is that the nodes are partitioned and stored on separate machines. And the fact that nodes only have access to their direct successors, right? So you only have the adjacencies list because there is no such thing as global shared memory. Okay, so how do we solve this problem? I'll give you a sketch of the algorithm to just get a flavor of how we've been able to do it. So Mike came up with a randomized solution. So what you do first is you assign a random and heads and tails to each of the nodes that you think are compressible, and then you simply have the head nodes seek out the tail nodes and have the tail nodes pass their adjacency list back to the head nodes, and thereby compressing the graph. And so it looks something like this. So you do a randomization, you do one round of compression, you get down to something like this, and mutate the graph structure of the process. You do another randomization and another round of compression, you get to something like this, and then like this. By this time, you can fit it in memory, and then you put it, compress it the rest of the way. Okay, so that's just a sort of a flavor of the types of things that he's implemented in MapReduce. So here's some results. So he's built a system called Contrail, a de novo assembly of a human genome. In this case, it was an African male. Input about 3.5 billion short little reads. And so here's some initial results. Starting from an initial graph about 7 billion nodes. Once he applies the graph compression, he gets it down to about 1 billion nodes. He has other couple tricks. So for example, there's a lot of spurious tips, he calls them, based on sequencing errors. He can clip that fairly easily. Based on sequencing errors, he also has what he calls bubbles, and he can pop the bubbles. And he can do quite well in graph simplification. Okay, so here's another case study of MapReduce being applied to quite a different problem domain. Okay, so and there's a manuscript currently under preparation, and so you'll read about it soon. Okay, so let me start wrapping up here and sort of talk about where I see the future and where's this all going. So MapReduce is the best thing since sliced bread, right? No, I actually don't believe so. Right? So. It's all about different distributed programming models, as many of the speakers before me have talked about. MapReduce is probably the first successful one at scale. It's definitely not the only, and it's probably not even the best. And there are lots of alternatives out there. So for example, many in the open source community have talked about, well, MapReduce is actually too low level. We should be programming in something that's higher level. So Pig is something that tries to fulfill that need. So you can think of Pig as Perl scripting for peta-size scale data sets. Of course, you've heard also about dry and dry-at-link from Microsoft, the directed acyclic graph model of computation. Google recently talked about something called Prego, which is their framework for large-scale graph processing. And so I think the key here is it's all about finding the right level of abstraction. I mean, what clearly hasn't worked, I've argued, is that the von Neumann architecture just is not cutting it anymore in this multi-core data center cluster computing world. And so that's why I think one important point. The second point is this separating the how, the what from the how, and I think that's a very important insight. And then this goes back to the comment I made earlier about I want my students developing machine learning algorithms, not debugging race conditions, right? So I think this is really the key. We want a developer to be able to sort of specify the computation that needs to be performed, and then have a execution framework just go and do the execution in the cloud for us. And having the framework hide system-level details from the developer is going to make applications developer far more productive. And so if you really believe that the data center is the computer, the collective question that we'll be trying to answer in the next few years is, well, what are the appropriate abstractions for the data center computer? Okay. Something I haven't touched on, which I think is also important, is the educational aspect. And so how do we teach our students to be able to think at a petabyte scale? That's an important question. That's something I've devoted some effort to. It's something I've actually had some successes in. So I've been running a series of MapReduce courses targeted at intro, master's level, advanced undergrad level. And in fact, the first case study that you heard about, the one in statistical machine translation, was actually a course project collaborating between grad students and undergrads that was done in a course of a couple months. Michael Schatz also was one of the early takers of my MapReduce programming course, and I think it's fair to say that the work that I presented sort of was was inspired by some of the stuff he found out in my class. So that's about it. I want to leave everybody with this final thought. So if data is the rising tide that lifts all boats, then this commoditization of large-scale processing capabilities allow us to rise up with the tide. And if we can, why wouldn't we? Right. So I'll be happy to take any questions, and I'll welcome your feedback.
Okay, we have time for a few questions before we all move across the hall.
Yeah, don't ask questions. Let's go see Avatar.
So one thing that always is a big rub in these kinds of systems when you talk about large data is that large data isn't at all portable. Mm-hmm. So if it's generated in California and you have several petabytes and you want to do the computation somewhere else, you need to take the hard drives and send them to that somewhere else. Yeah. So do you have further thoughts about that as the data grows and our bandwidth on that data it travels away from the computation exponentially? Mm-hmm. We need other ways of moving data around.
Okay. You want the tongue-in-cheek answer or the serious answer? The tongue-in-cheek answer is, well, a couple sessions back, you heard about data centers and containers, right? So why couldn't you, if you wanted to move a couple petabytes across the country, park a container next to the thing you want to transfer it over, put it on a flatbed, drive it across the country, and reverse the process. So that's sort of the tongue-in-cheek answer. Yes, I think that's a serious problem, and I think a lot of it, at least for the stuff that I'm interested, is remedied by the fact that I can do the computation where the data is gathered. Right, so I work with web data. Well, it's being crawled somewhere, and so might as well do the computation on the cluster in which the crawl is being generated from. Same thing with log analysis if you access to log data. So it's certainly not the general case. But I mean, back to my tongue-in-cheek answer, I wouldn't underestimate the from
from what I've heard, Amazon, you can ship them hard drives, and they will, handle it just like any other package that they handle, and load it onto their service for you, for example.
Well, that only works if the ratio of the compute to the data makes sense for you. So if it costs you more time to send it, then you might as well run it here.
Yes.
On one node rather than sending it there.
Yes.
On 10,000 nodes.
Yeah, but for large data stuff, I think that is always going to be, that ratio always works out in your favor, that you want to ship the data.
Another actually point on this is that I think a large collection of large data will be built by accumulation into data centers. And if it trickles in, it builds up quite rapidly in some cases, and you have it right there. Web crawling is a good example of that. Yeah. So the type of data that Jimmy looks at, text data, is stuff that's been harvested really on.
Yeah, the other joke I like to make is I made the suggestion that for these people that work on bioinformatics is that they should just move their sequencers to where the data centers are, right, and send the samples over to the data centers, and so that you have a direct pipe from the sequencing machine into the data center.
Yep, you have to co-locate.
Yep.
Okay. Oh, we do have one more question.
So my question is around your bioinformatics part. How real is your actually assembler? So it means, do you take into account continuous quality data? Do you think about having longer reads, like 200 base pairs? Or do you think about estimating repetitive regions? Because, I mean, this is a very nice example, but in the real world, it's actually a little bit more complicated.
Yeah, so the reads are getting longer, but I don't think the total amount, I don't think the problem is easy. You're sort of...
I mean, the key here is quality data, because it's not... It's not 0-1. It's actually at the beginning of the sequence, it's better quality, at the end it's worse. But you usually combine between something good and something so not good, or something in between.
Yeah, I think you've exhausted my knowledge about bioinformatics. So I could certainly put you in touch with my colleagues, but I don't think.
So, but I mean, my question is, was it actually designed as an experiment to prove the concept, or it was designed as a real life application?
A little bit of both. And I actually don't know the answer to your question on whether or not quality data was taken into account.
And one comment about the sequencers. Actually, the sequencer data is not that big as it looks like, because what we actually deal is actually a string of ASCII characters that is for DNA. The huge data that everybody talks about sequencing is actually pictures, images coming out of the sequencer, which never go far from the sequencers, because you cannot do anything with them.
Yeah.
All right, I think at this point we've got a 10-minute break before the show starts in the next room. Thank you all very much for coming to these sessions. Thanks, Jimmy. Yep.